All right, so questions.
I'm having a hard time passing that dictionary character variable to a function.
Okay.
And I'm just wondering how you go about doing that.
Sure. Let's play with some code. Alright, so this is going to be junk code, but we'll get the idea. So there's a dictionary array. It's 1,000 entries. Each entry is 201 characters long. Alright, so we're just going to seed this array with a couple of strings just to make sure that this works. So we'll use string copy, which is part of string.h, to copy things into those first 3 entries. Is that me? Okay. That's okay. Whoa. Hit the wrong button. Okay, then let's just pass this to a function to print out the contents. So I'll prototype this function. I'm going to prototype it like that. Alright, so I'm declaring the argument exactly 1,000 by 201. This will only work if the thing I pass to it is 1,000 by 201, which I said you can assume. Right, that's the only size we need to worry about. And so let's try a for loop 0 through 2, and we'll print out phrase I is, and we'll show the value of that array bracket I, which should be the ith phrase in there. And I believe this will work. Or it will blow up horribly. Alright, we'll fix those in a minute. That's perfect. Alright. So yeah, prototype it again with character 1,201. Use that in your declaration of it, use that in the definition of the argument and the function. Stick to that everywhere and it should just work directly.
Yeah, I was getting a lot of errors, and I was saying declare it as have like a star in parentheses and the 2 brackets at the end.
Yeah, so apparently if you use star star you get strange things like this.
Yeah.
Yeah.
Like that, yeah.
So yeah, just make it always character bracket 1,000 bracket 201.
Cool. Thanks.
And you can do it more generally with the stars and stuff, but it does make it more complex, and I don't want to get people bogged down in that for this. So we'll take that kind of thing apart in 222 and see ways to do it. All right, other questions? Yeah.
Can you explain why car star star doesn't work?
A car star star is different. Even though we think of arrays and pointers as being the same thing, there's actually subtle differences between them. When we say something is a car star, we're just saying it's a pointer to a character. When we say something is a character or an int bracket 100, we're specifying how large it is. We're saying that this chunk of memory already exists, and at some level they're identical. They shouldn't make any difference, but the compiler definitely cares. It's just complaining that, you know, we've told it it's a car star star, but then we told it later on it's a character 1201. They're different things, and it has to do with this question of how we store these things internally. And yeah, I don't want to get too deep into it right now. But if you have a two-dimensional array, you kind of have to know how wide it is to be able to figure out where element I comma j is, because you have to go over a certain amount and come down. And if you have a car star star, you don't know anything about the width. If you make it car bracket width and then a star, it can still resolve those indexes. But the explanation beyond that's going to be more confusing than the enlightenment. But if you really want to know about it, catch me in office hours and we'll go through some sample code. All right, anything else? All right, so I posted an ODP for today. So this is 418. And you're making a function called move, and just like our last few ODPs, it takes two arguments. The first argument is the input string, the second argument will be the output string. And those already exist for you. Okay, your goal is to populate that output string. Okay, and what you want to do is take the input string and basically shift it left one spot and take the first character and copy it over to the end. So if your input is HELLO, your output should be ELLO and then the H at the end instead of the beginning. And there's no super slick way to do this. You have to do it by hand. You have to basically take each character and put it into its correct position. And if you try to do that, it's fairly benign. So here's your input string. So let's say we call our arguments in and out, and this might be our input string. It's 5 letters, it's a null terminator, and then we don't know what else is in there after that. And our output string, assume it's initially a bunch of unknowns. So what do we have to do? We have to take this character E and copy it into here. Take this character L, copy it into there, L, O. And then we have to take this first character H and copy that into the last spot. And then we have to put a null into the following spot. And if you just do those 3 things, your code will work perfectly. Right? Copy every character starting with the second character into starting with the first character. So copy character I into I minus 1, up through and including the last character. Then copy the first character into where that last character was in the original string, and then copy the null terminator into the right spot. But make sure you copy the null terminator. Make sure you don't try to use string length on out, because right now if this is out and I do string length, I'm going to get some big number. Right? You can use string length on in, and that'll tell you where to put the null terminator in out. Okay, but make sure that what you're doing works with your sample variable values. And watch out for the case where you have an empty string. If you have an empty string, then really you just want the output to just have a null terminator in the first position and you're done. If you have an input string with just one character, the output string is going to look exactly like the input. And so I would just copy the output to the input. If you have 2 or more characters in the input, then you can start doing some kind of for loop to shift these things over into the output and then move the first character. So you may need sort of 3 separate cases. And then in the most general case, you have sort of these 3 things to do. So as long as you're clear what your algorithm's going to be, and you test it out in those edge cases as well as a general case, this should be pretty straightforward to code. But thoroughly test your code on paper. Make sure that it's doing the right thing. And then run it against some test code and then assess it. And if you're using test code, I strongly recommend initializing your output to something like, 10 question marks. So you don't accidentally stumble into a case where you had a null pointer that you didn't create.
We're returning an int. Are we returning anything specific on the int?
I don't think it matters what you return.
Okay.
So pick your favorite int. And you can use string length. Don't use anything else. Anything else from string. All right, other questions on that? All right, I will try to finish grading your programming assignments 3 today, tomorrow at the latest. I wanted to get them done over the weekend, and it was a trying weekend, so I didn't get through. I got through about half of them, but they're looking really good so far. So I'm confident the others will come out looking really good as well. So nice work so far on those. All right, any other questions? So let's talk more about PA4. So I've suggested modularizing this, right, breaking it into pieces. And I've also said you need to include a makefile. So let's talk about makefiles. And let's talk about different ways to compile pieces of code and make them work together. All right, so let's see, what do we got here? All right, this is our stick playing game. And I've broken it into 5 pieces of code. So let's take a look at this. So here's my main program. And we kind of looked at this already when we did the programming assignment. So here's my main program. It calls a function called start, gives it argc, argv, gets back number of sticks. If number of sticks is 0, there was a problem, and so it returns, which exits the program. Otherwise, number of sticks is the number of sticks that the user specified on the command line or that they typed in when it said how many sticks do you want to use. we show the initial pile of sticks by saying show sticks, and then we play the game by saying play game, and then we just return, and that exits the main program. So this is highly modularized, right? The main program is 1, 2, 3, 4 real executable lines of code, and that's the whole game, right? So it uses these other things like start. So start.c is 53 lines of code that I don't have in my main program. It's buried in this function. So this checks argc. If it's too big, we give an error and return 0, which means error. If it's equal exactly to 2, it means that the user specified the number of sticks on the command line. We call s scanf. I should have used a %s, but I didn't. We check the return value to make sure it's a valid integer, and if it's not, we print an error message and we return our flag 0 again. Otherwise, they did type in a number, but if it's not at least 1, we print an error message and we return. So this is slightly different spec from what you actually did for the programming assignment. There's also a maximum number of sticks we can play with, and if the number of sticks is too big, we say too many sticks, and we exit out with an error code. Otherwise, everything is legal, we return the number of sticks. If they didn't put an argument on the command line, then we ask them how many sticks do you want to play with. We do an fget, we parse, we make sure it's a positive integer, and if it's not too many sticks, and if everything's fine, we return the number of sticks. So all that's hidden inside this one function called start. All right, and then we show the number of sticks by calling the show sticks function, and that's just a loop. And it prints out n pipes followed by the number of sticks in curly brackets. And then we play the game. And that's shorter than the startup, actually. So it's a while loop. Get the user move, subtract it from the number of sticks, see if somebody won, show the pile of sticks. Make the computer move, subtract from the pile of sticks, see if somebody won, show the sticks. And we just loop there forever until somebody wins, at which point we return. And this uses the get user move function. Which asks you how many sticks you want and make sure it's between 1 and 3 and keeps doing things until that happens. And here I used a flag instead of an infinite loop, right? I said, well, we have to do more, which I initialized to 1. And if your number is illegal, then we give an error message. Otherwise, if it's legal, we set do more to 0. And the next time we come up to the top of our while loop, we will exit, and we come down here and we return. So that's the details of the code are not critical, right? But I want to give you an idea of how this is set up. Basically, main calls a bunch of things, and some of those things call other things. Okay, so it's heavily modularized. So here's one way we can compile. We can say gcc-o main star.c, and that should compile everything. And then if we run main, it'll just do its thing. Right, and I lose as usual. So that's one way to compile it. What this does is it says take every .c file, right, which is these 5 files, and compile them. So go through the C code, convert it into an internal format, convert that into some sort of assembly language, put together all the calls and everything. So here's get user move, here's main. Main has to call get user move, figure out where this is in memory, load the address into this call over here, link everything together, in other words, and ultimately create an executable file called main. All right, so a few things. I did not prototype any of these functions. Right? I didn't say what type of argument start expects or what it returns or what show sticks expects and so on. I don't have any prototypes written up there. I also never defined that variable max sticks that says how many sticks can I take. But I do have a new include file. I have include stick.h. So let's take a look at that. Stick.h, that's got my function prototypes in it. Why did I put my function prototypes in there? Because these functions get used multiple places. Showsticks gets used in main, it gets used in user move, and so on and so forth. And I didn't want to type these in every place that I needed them. So I put the prototypes into this one file, and then when I say include stick.h, what that really does is says take all of this, these 6 lines of code, and pop them in right here. So if I simply took those 6 lines and typed them in right here instead of that include stick.h, exactly the same thing. Now I don't want to take my actual code for, say, start or show sticks and put that in a file and include that. If I include C code, then that C code is basically written inside my main.c file. And I don't want to do that. I want to keep my files sort of as small and single purpose as possible. But function prototypes, you've always got to specify. If you're going to use a function, you got to prototype it. So I'm going to go ahead and include that. My stick.h also includes this definition of max sticks. Well, I don't use that in main, but it doesn't hurt to define it. So I go ahead and I put that in here. Now I could make a second include file, but that starts to get to be a pain. I really want just one include file, and I'm going to include everywhere that I need to use any of these things. Start.c. So start.c needs to use this max sticks, right? And it gets that because I defined it in stick.h. Now I could have just defined max sticks in here, but then if somebody wants to work with this code and wants to change it and let it play with up to 100 sticks, they've got to know where that define was set up. By putting it inside a single file, sticks.h, right, anything that I want to do to customize this executable is available inside this one file. And like I say, it doesn't hurt to define things that you don't use. It takes a little longer to compile, but it's not much. It doesn't hurt to prototype functions that you don't actually call. So main thing you want to put in .h files, function prototypes and defines. Okay, don't put in executable code. Don't put in the actual functions. Don't put in things that call printf or gets or things like that. Okay, just the prototypes of functions and anything you want to define. So every one of these .c files includes stick.h if it's calling any functions or it needs to use max sticks. Okay, so that's one thing we want to do. We want to put an include file in there. And the nice thing is, if I suddenly have a new function, or I decide that one of these functions should have a different argument, I don't have to change that prototype in 5 different files. I just change it in stick.h. All right, so we're centralizing. So CPP, the C preprocessor. This is a macroprocessor that is automatically used by the C compilers. You transform your program before compilation. Okay, this is always run. Anytime that you say GCC, before your code gets compiled, it gets run through what's called the C preprocessor. And the C preprocessor does things like deal with defines. And that's really, and include files. So those are the 2 main things that we do. We have these things that start with a number sign include, and number sign define. Does everybody know what define does? I haven't really talked about it. Define lets you set up a macro, basically a symbol substitution. So let's just do this. Alright, so I'm going to define message to be the string quote hello Nick exclamation mark backslash n double quote. And if I say printf parentheses message, this symbol here, message, gets replaced with all of this. And if I change message, right, then it'll print something different. But if that was a message that I wanted to print a lot of different places, I can define it once with this define statement. And now anytime I want to print out message, I just say printf, and it's uppercase message. When the compiler actually starts to compile my code, here's what it actually compiles. Right? It gets rid of that printf parentheses message and replaces it with printf parentheses double quote hello Nick double quote. Okay, before it actually does any conversion from C, it goes through and it replaces all of these defined things with what they're defined to be equal to. That's the preprocessor's job. So this never gets to the actual compiler. This gets to the compiler. Same thing with number sign include. So here's your source code, which is file.c. That goes through the C preprocessor and gives you bigger source code, but it's still just C code. That goes through a compiler and gives you object code, which is a .o file, and that goes through a linker and gives you an executable. Actually, I cheated. This compiler actually goes down to assembly, and that goes through an assembler and gives you object code. It may not actually do that though. It may go directly from C code into object code, but in kind of a theoretical way. Here's the full path. Source code goes to the preprocessor, gives you bigger source code, goes through a compiler to give you assembly code, goes through an assembler to give you object code, goes through a linker to give you executable code. All of that happens by just saying GCC. So that runs through all those steps, but those are the things that are happening internally. Okay, why do we care about this? Because all of this is very time consuming. So this is slow. And this step down here, this is fast. There's less work to do. And everything that the linker is dealing with is in a machine readable form. It doesn't have to break out comments and ignore them and go through lines of white space that don't do anything and convert things from human readable form and figure out variable names and stuff like that. The stuff has been pre-digested, and here it's in a form that's really easy for the machine to deal with. And the linking step is pretty efficient. Okay, so if we have a bunch of C code and we want to link them all together to make executable code, if we take each .c file and turn it into a .o file, that takes a long time. And when we say something like gcc -o main star.c, right, we're listing 5 .c files. Each of those C files gets pre-processed, assembled, compiled, right? And that's time consuming. And then we get those 5 object files and we link them together and we get our executable that's fast. Okay, that's all motivation to say there's a faster way to build programs. So if I say gcc-c getusermove.c, that makes a getusermove.o. So my .c file has been pre-processed, it's been compiled, it's been assembled, we have the object file. Let me get go out of the way here. So if I compile all my .c files, I get a .o file corresponding to each .c file. Show sticks.c to be bogus. All right, if I have those object files, I can turn them into an executable file like this. And that just takes those 5 object files and links them together. And I've still got my runnable main program. Okay, why is this better? Suppose that I want to change my main program and I want to print out a greeting to you. Alright, so I'm adding a print statement in the beginning because I read the assignment and I realized I forgot to do that. Okay, this is a small program. Compiling this into an object takes almost no time. It's a half dozen lines of code, right? That's not a big deal. But all of my other code has, you know, lots of lines of C in it. Okay, it's not that many, but about 100 lines of C code in everything else. I don't need to recompile getusermove.c. I don't need to recompile showsticks.c. I don't need to recompile start.c. Those aren't changed by my change to main.c. Right? The only thing I did was I added one print statement to the beginning of main.c. I don't need to compile any of these other files. I've already compiled them once. And the code doesn't change. So the .o's that I already have from compiling these .c files are still usable. The only thing I need is to recompile my main and make a new main.o. So I can say gcc-c main.c. And now I can take all of my .o's and link them together to make a new main. And now my new main program has this print statement in it. So what's the goal here? You have your program, you have 100 different modules. You change one module, how do you rebuild your main program? You don't really want to compile all 100 C programs. You only want to compile the programs that actually were changed by whatever editing you did. Probably just the one file that you edited. So you want to compile that back to an object and then link all of those together. But suppose I change stick.h. Suppose I edited getUserMove to take an argument, which is how many times you can try to answer the question, how many sticks do you want to take? So you can say getUserMove 2, and it'll only give you 2 tries, and then it'll say, you know, you don't know how to play, goodbye. So I'm going to change getUserMove. Well, now I need to change that prototype. Well, I can do that in here. I could change this to getUserMove parentheses int. But what has to be recompiled now? Anything that includes stick.h. Right? So I can, you know, go barehanded and just search for stick.h in all of my .c files, and now I see there's 3 things I need to recompile, right? But imagine that this program consists of 100 or 1,000 different modules, and some of them use things from other modules and some of them don't. And maybe there's 3 or 4 include files, and some of them include those files and some of them don't. And you've downloaded this package from the web because you really want to play the stick game, and you're trying to build it, but you want to make a change and you want to know, how do I compile this? And maybe you can just compile all 1,000.c files and link them together into a main, but probably not going to work, right? And these things get really complex. Okay, so the sort of ultimate example, think about the Linux kernel, right? Trying to recompile the Linux kernel. This is something you used to have to do a lot in the early days of like Red Hat Linux. Anytime you wanted to do something interesting, they always said recompile your kernel, right? And there's no way that you can figure out exactly what should be compiled. And when you compile with GCC, you can put switches on there. You can say disable bounds checking, but add checking for buffer overruns, and use the options from C99. So there's a way that when you write a program or build, a project with a bunch of source files and stuff, that you can specify exactly how things should be compiled and how things should be recompiled when something changes. And usually when you download something from the web, you get a bunch of source files, you get some include files, you also get this recipe that says, how do I make my executable? Okay, that recipe is called a makefile. And a makefile is really just it's a recipe. It says what depends on what, and if you need to rebuild something, how do you do it? So Makefile is called Makefile. That's got to be the name. And I'm going to use my little trick. I'm going to read the output of the command ls*.c because I don't remember what my file names were. So I'm going to read that into here just so I have these things available. And I'm going to join these onto a single line. Okay, so that's just for reference. So let's make a Makefile. So what does a Makefile look like? It's pairs of lines. Okay, it's a plain text file. Your lines come in pairs. The first line has what's called a target, a colon, and dependencies. And the second line begins with a tab and is followed by what's called a recipe, or let's just say a command. And then the third line is another target and dependencies, and then a tab and a command, and so on. Okay, target is the name of something that you are trying to build, typically main or kernel or PA4 or whatever. Dependencies are files that need to be up to date in order to build whatever that target is. And then the command on the next line is the thing that you do to build that target once the dependencies are satisfied. So really confusing to describe, pretty simple to see, so let's just write some code. So the main thing I want to build is, let's just call it stick, colon. And in order to build stick, I need to have my 5 object files. So stick depends on get usermove.o, main.o, playgame.o, show sticks.o, and start.o. Does stick depend on stick.h? I mean, it would seem like it does because that's an important include file, but if my object files are all up to date, I don't need the include file anymore. I only need the include file to compile, say, main.c into main.o. But if main.o is up to date, that's all I need, right? Those 5 objects. So I don't really need stick.h here. Okay, if all of those things are up to date, I'm going to type a tab and I'm going to type in the command I use to build my stick program, gcc-o stick, and then I'm going to do some vi fast magic. So then I put in the 5 objects that I want to link together. And there's my command for building stick. All right. When I say make, the first thing it's going to do is look for the first target in the file, the name of the thing on the very first line. It's going to say, oh, he wants to make stick. Okay, what needs to be up to date? These 5.0 files. If it finds those .o files in the current directory, it will go ahead and it will execute that GCC command. But if all I've got is the .c files, there's no .o files, it's going to say, hey, that's an unmet dependency. I need to have a getUserMove.c and a getUserMove.o, right, in order to execute that first recipe. So where does a getUserMove.o come from? It comes from this .c file. So getUserMove.o depends on getUserMove.c, and I think it also depends on stick.h. Nope, it doesn't actually. So it only depends on getUserMove.c. And if that exists, here's my command. Just gcc-c getUserMove.c. So I've got 2 recipes in my Makefile so far. The first one is for making the final executable program stick. And it depends on the 5 objects, and there's a command given those 5 objects to build stick. The second recipe is for making the object getUserMove.o, and it depends on getUserMove.c, and if it exists, there's the GCC command for turning that into a .o. So I have to do this for each of my desired objects. With me so far? Alright, so it looks like main, playgame, and start.c depend on stick.h. So main, playgame, and stick.c. Start.c. Alright, got the idea what we're doing here? It's a prescription for building stick depending on these other things. Alright, let's see if we messed anything up. So let me get rid of my .o files. So I've just got my, and let me get rid of main. So I've just got my .c files and my .h file and my make file. Okay, so when I want to build this, all I've got to do is say make, and it shows me what it does. It does a gcc-c on my 5.c files, and then it does gcc-o stick and getUserMove, all the .os, And now I should have an executable program called stick that runs my code. Now if I again say make, it tells me stick is up to date. There's nothing that has to compile because nothing has changed. Okay, let's change showsticks.c. Let's just add a comment in the beginning. Okay, showsticks.c has been modified. What do I need to recompile to build my sticks program? I don't know. But if I say make, it will recompile showsticks.c and it will link my objects together to make an executable. It did not recompile main.c, it did not recompile playgame.c, and so on. It just compiled showsticks. And again, if I say make, stick is up to date. Let's change stick.h. Let's just add a comment in the top. And now if I say make, it recompiled 3 of my .c files. Which 3? The 3 that depend on stick.h. How does it know that? Because when I made the make file, I told it what those dependencies were. So you build a make file to go along with your project. As you create modules, you update your make file. But once you've got a make file in place, anytime you want to recompile, all you got to say is make. You never have to say GCC again. You never have to think what depends on what do I have to recompile, did I change this file yesterday? You just say make and it'll take care of it for you. And what it's doing is it's looking at the timestamps on these files. And if the timestamp on showsticks.c is newer than the timestamp on showsticks.o, it decides, oh, you've changed the source file since the last time you compiled, I better recompile. And so if I try to make stick and it needs showsticks.o, it will see what showsticks.o depends on. It'll check showsticks.c. If that's more recent, it'll say, oh, I better remake showsticks.o first. It'll execute that command, and then it'll go ahead and use that to build the executable. Okay, so that's probably about a 10,000-foot view of Makefiles. We'll drill into this more tomorrow. I'll show you some of the nuances with this, and we'll talk about how you can practically use this in your day-to-day programming work. All right, so we'll continue with this tomorrow.